Okay, now let's look at the backpropagation training algorithm. So, and let's consider a single hidden layer for simplicity to make sure that we cover or understand properly how it works. So again, the architecture, so you have, in this case, an input layer. Sorry, that was on purpose to wake you up. So this is the input layer or input pattern, x1, xi, xn. You have the hidden layer, the z's. So the x are the input, the y are the output layer, are the output nodes or output perceptrons. And the middle, you have the hidden layers or hidden nodes, which are denoted by z. So x, y, and z in the hidden layer. And then the Vij are the corresponding weights. So the weights between the input layer and the hidden layer, or the Vij is, you can say, these are the weights which are coming to node J. So you can see sometimes we put the node here or here, okay? So in this case, we're talking about node Zj, and the weights, the corresponding weights for that node Zj are denoted by Vij. So where I goes from 0 to n. So for example, in this case, V0G is, J is coming from this node here. V1J, you have Vij, you have Vnj, okay? And then the same thing for Wjk are the weights for node Yk. Okay, so the V are for these hidden nodes, the W are for the output nodes, and the K again, so Wjk, your J goes from 0 till, in this case, P, because you have P hidden nodes. So notation, X is your input training vector. So you have a training data set. The T or target is the output target vector. So that's your output. So that's what you get here. The X is, this is the input pattern. At the output, you get it. So you have the actual output, the Y's, but you have a target or desired output, okay? The delta K is the portion of error correction weight for Wjk that is due to an error at an output unit Yk. So at this output here, you're going to have a certain error between the desired output or target output and the actual output. And then it's going to generate a delta K, and this delta K is going to adjust the Wjk. It is a portion of the error correction. It is also the information about the error at unit Yk that is propagated back to the hidden units that feed into unit Yk. So this is what is propagated back from here, okay, from the, as it says here, the information, the error at unit K that is propagated back to the hidden units. So it's propagated back to these hidden units here. We're going to see in more details with an example. The delta J, so you're talking about, this is delta K for the output. So delta J is the portion of the error correction weight for vector, for Vjk. So this is, so here you have delta K, here you have delta J, okay? That is due to the back propagation of error information from the output layer to the, from the output layer. It is due from the, from the output layer to the hidden unit. So from here, from the output layer to the, from the output layer to the hidden unit. Alpha I think there is something going on here. We come back to this later. It become clearer. Alpha is the learning rate. We saw that before. V0J is the bias on the hidden unit J. So this is your V0J because you have a bias. So we put here a 1 here to accommodate for the bias. So we don't have in our activation function, the threshold start at 0. And then the W0K is the bias on output unit K. This is the W0K. So W01 will be the bias for node Y1. W0K is the bias on output unit K. So again, the activation, the type of activation function we had before, we saw that this is a binary step, which is 0 for less than when the input is less than a certain threshold theta, and then 1 when it is greater than the threshold. Okay, this is the formula. But our activation function, when we want to use the backpropagation, we want these properties to, we want the activation function to have these properties. We want it to be continuous, differentiable, and monotonically non-decreasing. And we also want its derivative to be easy to compute. So if you remember before, we saw this sigmoid function between the unipolar between 0 and 1, which takes value either 0 or 1. So that was the formula for it. And then it satisfies these criteria. It's continuous, differentiable, monotonically non-decreasing, and the derivative is easy to compute because the derivative is the sigmoid itself times 1 minus the sigmoid function. So it's easy to compute. And now another one is the hyperbolic tangent, which goes from -1 to +1. It has the same properties here. It's given by this expression here. And again, the derivative is 1 plus the hyperbolic function times 1 minus the hyperbolic function. So the derivative is easy to compute as well. So now let's look at the backpropagation training algorithm in detail. So we're going to look at it as an algorithm in a very simple way to be able to understand the process. So remember, this is our input pattern. This is for the corresponding biases. And this is the hidden nodes, the output, okay? So we initialize our weights. So the weights are around here. We initialize the weights set to small random values. And while stopping condition is false, so we are going to see that there is a stopping condition, we do step 2 to 9. So we start with step 2, and then we cover here 4, but then we're going to, in the next slide, cover the remaining one. So for each training pair, so we have a training set, which is labeled, for which we know the target output. So for each training pair, an input and corresponding output, each input unit, xi, I from 1 till n, because we have n of them, receives an input signal xi and broadcasts this signal to all units in the layer above, the hidden unit. So it takes the input here, propagates it forward. Another step is each hidden unit, zj, each of these units from 1 to p, sums its weights. So it takes the input multiplied by the v. Remember, these are the weights from 1 till n. And this is, we're talking about node j. Okay, so this is z and I and j, plus the v0j. V0j, which is this for this node j, is this bias. And then once we compute the net activation, we apply the activation function to compute its output signal. So the signal, the output signal, which is at the output of this node j, which is given by f of the activation, where f is the activation, one of the activation functions that we just saw in the previous slide, which can be a sigmoid or a hyperbolic tan, for example. Now we send this signal to all units in the layer above. So once you get the outputs here at these nodes, you send it to the output units or nodes. Now step 5 is each output unit, yk, from 1 till m, sums its weighted input signals. So if we take this node here, it takes all the inputs from, it takes the inputs from all the nodes from the hidden layer, multiplied by the weights. So this is, and then you add a threshold W0K. So this is the activation Y in K at node YK. Same thing, you apply an activation function, as I said, sigmoid or hyperbolic tan. Now we backpropagation, backpropagation of the error. So we take that YK, we compute it, we compare it to, so we take this YK, we compare it to the TK, to the desired output at node K, at this node K here. So each output unit, YK, K1 till M, so in this case we have only one, receives a target pattern corresponding to the input training pattern. So we have a target pattern, desired pattern. We compute its error information term. So this is the error information term. If you remember the learning rule, so it's TK minus YK. So the target output minus, or desired output minus the actual output, times the derivative of that Y in K. So it is the net activation at YK, okay? But then we take the derivative at that thing. And remember, for a sigmoid, it's F times 1 minus F, okay? And then we calculate its weight correction term used to update WJK. So we compute the weight. Remember the W's are here. So the delta WJK is equal to alpha, which is the learning rate, times this delta K, times ZJ, this ZJ. Because this is between node ZJ and then node YK. So it's between hidden node ZJ and then output node YK. And then we calculate the bias correction term used to update W0K, this W0K, using the same formula, but it's alpha delta K in this case, because we don't have Z, the corresponding Z is equal to 1. So we have a 1 here. So it's about the same formula here. Now we send delta K to units in the layer below. So we take this delta K, this portion of the error of the weight of this error, we propagate it, we send it back to the layer below. Remember, we're back propagating this error, or this portion of the error. Now each hidden unit, Zj, 1 to P, P of them, sums its delta inputs from units in the layer above. So we take the delta I and delta, so we take, for this node here, Zj, the delta I and J is equal to the sum of the delta times the WJK. So you take this weight here that we computed that we had before, initialized, and then we multiply by the delta K. It's just like, because we're back propagating. And then we multiply by the derivative of its activation function to calculate its error information term. So we take this term here and we multiply it by f prime of z in j. Remember, the derivative of f prime is f times 1 minus f for the sigmoid function. And then we calculate its weight correction term to update Vij later. So we update Vij, which is the weight between node xi and zj. Okay, so that's this delta Vij is equal to the learning rate xi, because this is the weight that we want to correct between node I and j, or actually input node xi and hidden node zj. So we look for this delta j for that node zj, and we calculate its bias correction term using the same formula, but in this case, the xi is equal to 1. Now, once we finished with the deltas and the backpropagation of the deltas, we compute or update the weights and the biases. So each output unit yk, so this output yk, 1 to m, update its weight, its bias and weights, so from 0 to p, using this formula. So it's the wjk, the weight between this node and this node, is equal to the old weight. Remember, we had initialized them initially to randomly, plus delta wjk that we computed before. And then each hidden unit, zj, 1 to p, updates its bias and weights using this formula. So the weight between zj and xi is given by the new weight is given by the old weight plus delta Vij that we computed before. And then we test with respect to see if we have if our stopping condition is satisfied. And then we're going to see later what is the stopping condition. We can test until, we're going to look at the stopping criteria. Okay. Let's examine the training algorithm equations. So in this case, instead of writing, with just numbers and so on between two nodes, we can write the whole thing in terms of vectors and matrices. So you have here your input. So this is V21. This is the weight between node or input node X2 and between input node X2 and output node Z1. So vector and matrices make the computation easier. That's what we're going to see. So this is our input pattern, X1 to Xn. It's a vector. This is the weight matrix. So we have V11 to Vn1 for this node here. So V11, V21, V31, and so on until Vn1. So we put all for node, for this node here, we put all the weights in this column. And then for this node, we put them in this column. For this last node, we put them in this column. That's for the V. So V0, the biases, they're also given by this vector. So the step 4 that we saw before, computation becomes Zn equal V0. So it's this vector plus X, this input vector times V matrix. And the output Z, this is the net activation. And the output Z, you just apply the activation function. For the W, you have the same thing. For these W's, these weights, we have the bias vector. We have the matrix. Again, this is for the first node, the weights for the first node, second node, and M node, okay? And the step 4 before, computation becomes the bias plus Z, the output of the hidden layer, times the W matrix, this matrix here, the weight matrix between the hidden layer and the output layer. To find, this is the net activation. So to find the final output, Y, the actual, we apply the corresponding activation function. So now we would like to see, okay, when we do the training and using the backpropagation, we want to train with a certain training set. So, and then we want to be, we want the algorithm to be able to generalize to patterns that it didn't see before, and it should be able to give us good performance. So once trained, the weights are held constant. So once you finish the training, so the training is done offline, you stop training, you stop modifying the weights, and the input patterns are applied in feed-forward mode, commonly called recall mode or test mode. So you have a test data set, and then you bring it to your multi-layer perceptron, and you want to, and this test data set has never been seen before by the network, and you want to see if the network is able to generalize, either to classify or to do the regression properly. We wish the network to generalize, i.e. to make sensible choices about input vectors, which are not in the training set, so unseen input vectors. Commonly, we check generalization of a network by dividing the known patterns into a training set used to adjust the weights and a test set. And usually you have a division of 70-30 or so, used to evaluate the performance of the trained network. Generalization can be improved by using a smaller number of hidden units. Must learn the rule, not just the examples, meaning that you use a shallow network. You should not overtrain. So meaning that you don't want to overtrain to the point where the system just memorizes all the patterns. You want to be able to allow the system to generalize, okay? You want to ensure that the training set includes a good mixture of examples. So from all the classes, meaning that your training data set is balanced. So each class is represented, you know, with a good number of patterns, input-output patterns or examples, training set. And if you have a class imbalance, for example, where for a certain class you don't have lots of data, so there are ways on how to do it, okay? How to solve the problem. No good rule for deciding upon good network size. So it used to be very hard to, find the optimal number of layers, optimal number of units or perceptrons per layer to be able to get a good performance or the optimal performance and the optimal number of units. But now with meta learning, there are lots of approaches which allow you to do that. Even there are tools now, for example, Keras Tuner, which allows you to automatically find the optimal number of layers and number of units per layer. Actually, there are some really good references to explain this thing. Usually use one input-output per class rather than a continuous variable or binary encoding. Okay, that's detailed. Thank you.